Mm. All right, so let's start. It's 4:15. All right, let's start. And recently, my finger was injured, was hurt, and I cannot do my push-up today. So possibly we need to uh, take a break for a couple of weeks, maybe 2 weeks, and hopefully we can do it again afterwards. Okay, so let's start. So we don't do push-up today. Uh, Okay, just quickly remind you what we did last time. So last time we covered a circle, the length, and the sector. Right, couple of things we did. Some of the formulas that many of us know already. First one is the area of the circle. It's a pi r square, right? Circumference of the circle is a 2 pi r, no problem. Right, sector of how to find the sector. The area of sector is you first get a pi r square, so the area of the circle, right? And then, mm, so change the name. Okay, sure, I can allow you. So please, yes, change your name if you want. Right. So please use your name so that use your own name so that I know who you are. Okay, very good. Um, let's see. Now next, so we have the arc length. So the area of the sector is a pi r squared. That's the area of the whole thing, and divide by 360 and times theta, right? So it's just like a proportional, right? It's a proportional to the area of the sector. And then the length, the arc length of the AB. Again, I go over the whole revolution, 2 pi r, that's the circumference. And I divide by 360 and times and theta. So again, this is just a portion of that circle. And then we introduce two different angle measures. And many of us are familiar with the degree measure. But we also give you the idea of the radians measure, okay? Well, the radians measure basically says that for 360 degree, I'm going to consider that to be 2 pi radians. Okay, why do I want to do that? Well, later on when we study calculus, and you will see sometimes it's convenient to do that. So it's just a different system. Okay, 180, we can go from here, divide by 2. 180 degrees is similar to that the pi radians. 90 degrees is just a pi over 2 radians, all right? And in particular, 1 degree is pi over 180 radians, and 1 radian is 180 divided by pi, that many degrees, right? And then we did the conversion. That's easy. So I leave the work to you, right? Just multiply by a conversion factor, right? So that you can change from radians measure to the degree measure and vice versa. And then another one is um, if you go to the degree, and if you want the angle to be really really small, to be very precise, right? And then 1 degree is equal to 60 minutes, and 1 minute is equal to 60 seconds. It's not talking about time, it's just a degree measure. Okay, and then we can go how to change from the degree, minute and second system, and to just the degree and vice versa, right? And some of the formulas, again, in terms of the radians measure, right? For the radians measure, for the area, where this is let me slow down a little bit. This was the standard one, right? It's a pi r square and then divide by 2 pi. The original formula was 360, but 360 degrees is just like a 2 pi radians. So if my theta, the angle, was in terms of radians measure, I can use this so that you can see pi and the pi are cancelled out. So one of the advantages of this, of using the radians measure, is that the pi actually is cancelled out, right? So you can write that to be 1/2 time theta r squared. And then I can also rewrite that. So this is I like this one. I like this kind of formula. So this one is like 1/2 times the base and times the height. The base just means it's arc length, AB. Height just means the radians, right? So that's similar to the area of the triangle, right? That we did, many times, some time ago, right? So that's the area. And then we also have the arc length. The arc length is the angle times the radians, right? And we give you the definition of the following. If we talk about arc length, then the three arcs, A, B, C, D, and E, F, they're different. AB is bigger and EF is smaller. But if we're talking about the measure of the arc, the measure of the arc is actually a degree. It just means that, if you want to go from A to B, what's the angle change from A to B? And it's actually the same as the angle change from C to D and from E to F, just because they're similar, right? The three circles, they're all similar here. So in that sense, we can define the measure of the arc of AB and CD and EF. They are all the same. Okay, they are all the same. They are corresponding to the central angle. So that's a new definition. We probably don't know that before, but so this is a new definition. So that's a new definition. It's a measure of the arc. The measure of the arc has nothing to do with the length of the arc. The arc could be very long, but the measure of the arc could be very small, right? They're different. The measure of the arc just means it's an angle, right? It's an angle. All right. Very good. And we have some example like that. So a couple of examples. This is a good example. And then later on, we did some figure out the area of the shaded region. Right. These are some typical problems, right? So for example, this one here, we have a square and we have the two, we draw the two circle, right? And then how can we do that? So basically, it's a kind of inclusion exclusion, right? We add some pieces and try to delete some other pieces, right? So you just have to be careful when you do this, right? Next problem, similar in a similar way, right? Can you see that? So let me give everyone 30 seconds to figure out the refresh your mind, right? How do I get this shaded region, right? A, B, C, D, the square, right? And I have two a circle, right? One is centered at A, the other one is centered at D, and we get the shaded region. How can I get that the area, right? Here is the idea. The idea is that you just draw the hairpin line here, right? So first of all, I'm going to get I get this one here, right? So first I have this one. So this is what I get here, right? So I get a sector in with a center at A, and then I get a sector with a center of D, right? Adding them together, and you can see that where the triangle was doubly counted. So subtract the triangle. So that's how you can get the final answer. Does it make sense? Right? Okay. Finally, Let's see. Last time I just give you the just listed this, but I didn't prove that. I just say where you can prove by using congruent triangle, basically, right? Why? Let's think of that again. So suppose we have a circle here, right? And we have two triangles, OAB and OCD, and prove that the AB is equal to CD. Now this is not arc length. This is the length. This is a nine segment, right? The two nine segment, or you can say it's a chord, right? The two chords, AB and CD. The two chords are congruent if and only if the measure of the two arcs are the same. Excuse me. So why? Let's think of that. Why? Well, basically, you need to understand the arc in AB and CD. Arc AB means the angle of AOB, right? Arc CD means the angle of the COD. And so if you change the arc, the measure of the arc into the central angles, then it just becomes the comparison of the two triangles, and that makes things much easier. Why? So let's say, so if I have, um, so first of all, so if I have, uh, let's quickly prove it, right? So if I have like AB equals CD, right? And then I can say that this is equivalent to the triangle of the AOB is congruent with the triangle of the OCD. Why? Just because of side, right? Because of SSS. Why SSS? Because you first of all you have the radians to be the same already, so that's on the top, right? That's ON equals the OC, and OB equals OD already. So we have two pairs, right? Two pairs of the sides to be the same already, right? And so if I have the two chords AB and CD to be congruent, then automatically I can get the two triangles to be congruent, right? So they are just a if and only if condition, right? So if that's the case, then I can get the other one, the triangle of the angle of the AOB equals the angle of the COD. Again, it's a if and only if condition, right? Right. So maybe I shouldn't write in that way. Maybe write in a different way here. So this side is a SSS, and this side is actually SAS, right? Because you have the two pair of the radians to be the same, and then the included angle to be the same. So it's a SAS, right? Anyway, so that's from last time. Are there any questions? Very good. Okay, some people are waiting. Let's get them in here. Very good. So that's from last time. Now today, I'm gonna do let me just finish one more problem, and then I'm gonna start today's topic. Here is one more problem. So let's see. Okay, and let's see. Suppose we have a circle. All right, and then I'm going to have the center here, O, and then I have, let's say this way, and maybe this one here. So we get the A and B here are the 2 points from a circle, and I connect the AB. Okay, so let's say, suppose the radius of R is equal to 3, and I'm assuming that the measure of the angle is 120 degrees. Okay, you know that. So 120 just means it's a central angle, right? So it's a measure of the arc. And I want to find the following. I want to find the arc length. So this is an arc here, and then I get a length here. So at the two bars means it's an arc length. So this means the arc length, right? So this means arc length. Okay. Arc length. All right. And now I want to find the other one. What is this? This is just the length of the ninth segment, right? It's the length of the ninth segment. Length of the ninth segment. Okay, so give everyone a minute. So first, 180, just 120, just means that this angle, the central angle is 120. Everyone's okay, right? That's a definition from yes, from the previous time, right? The measure of the arc of AB is the same as the central angle of AOB. So this angle is 108, 120, and the two sides are 3 and 3. And then we are looking for the following, right? So let's see how we can get that. Uh, First of all, how to find the arc length? So to get the arc length, where I can have the first of all, I have a 2 pi r, right? And then divide by 360 degrees and times 120 degrees. Does it make sense? Right? So we can get that. And you can get the answer immediately. So this is 1 over 3, right? 120 divided by 360, that's 1 over 3, right? And then 2 pi times r is equal to 3. 3 and 3 are cancel out. So we can get the arc length of AB equals 2 pi. That's the first thing. Very good. That's easy. Second one, how could I get the length, the length of the ninth segment? All right. So anyone get the answer? Not yet. Where? Let's see. Well, it's just a triangle, right? So you have the two sides of the triangle to be 3, 3, and then and then the angle between them is 180. How do I find the other side, right? So let's see how we can do this. Okay, I'm gonna let me just draw from here. I want to draw where things because the OAB is isosceles triangle, right? And then you can draw the attitude to the base of AB, or you can draw. I want to draw the median, right? Or I want to draw the angle bisector. They're all the same, right? That's proved from the previous the 07 geometry, right? So from the previous class, right? Not semester. So if you just draw like the median, or if you draw the median, it has to be a perpendicular to the base, right? Or if you draw the altitude, it has to be the median, right? Those lines are actually the same, right? So anyway, so you draw that in the middle point, the midpoint here. So let me call that here, and H is also the midpoint. So you can get that here, right? So this is the let's see. So I'm going to draw OH perpendicular to the BC, right? If that's the case, then what can I say? Then basically, if I draw this, then I will say that triangle of OAH is congruent with the triangle of the OBH. Why? It's the HL, right? It's a HL. HL just means you have two right triangles, right? You have the hypotenuse are the same because they are 3, 3, and then you have one side. One side is just the OH, is a common part, right? So just because you got the OA equals OB, and also you have the OH is the same as OH. So that's HL, right? We can get that. And this implies that the AH equals the BH, right? Just because they're corresponding side of congruent triangles. Okay, so because of that, so if I want to figure out the AB, if I want to get AB is just 2 times, AB is just 2 times of OA, right? I just need to figure, no, AH, right? So it's just a 2 times of AH. And I just need to figure out AH. And that's easy because this is a spatial right triangle. Why is a spatial right triangle? Well, because first of all, oh, I still have to say one more thing here. The angle of the AOH, the angle of the AOH is the same as the angle of the BOH, and that's 120 degree divided by 2, and therefore that's equal to 60 degrees, right? That's equal to 60 degrees. So if it's equal to 60 degree, then the triangle is a 30, 60, 90 right triangle. So let me just draw that right triangle here, right? You can get that. This is A, this is O, and this is H. This is 3, right? 60 degree and right triangle here, 30 degree, right? And so the question here is that what is this? Where we know that we know how to do this, right? Because if I don't worry about if I don't have that 3, the usual idea is that this is 1, this is 2, and this is root of 3, right? So how could I get AH? Well, how could I get AH? Where AH, if I want to get AH, so AH over root of 3 should be OA over 2, right? Just because of the similar thing, right? Just because of similar things. So AH divided by root 3 is OA divided by 2. But what's the OA? OA is equal to 3 to here. So I can get basically from here, I can get 2 times AH equals 3 times root of 3, right? So I get my answer is 3 root of 3. That's the length of AB. All right, that should be okay. So there's nothing new here, right? It's just a kind of original problem. So these most of the ideas are from the previous semester, right? So 07 algebra, 07 geometry. Okay. Are there any questions so far? Very good. Now today, the topic for today is that where when we talk about the circle, the most important parameter is pi, right? Where looks like everyone knows the pi, right? Pi is roughly 3.14, and if you want to be more precise, some people can memorize many digits, right? Seems like that everyone understands the pi, but the problem is that how do you know how do I get the estimate of pi? How do you know the pi is equal to 3.14, like 15, like something like that? How do you get those digits? How can you make an estimate of that? Right, that's very important in the history of mathematics, especially many years ago, right? Many 1,000 years ago, how do you approximate the pi, or even 500 years ago, right? How do you do that? Before we have a powerful calculators or computers, how do you use hand to calculate, to estimate the pi? So that's the topic for today. So I'm going to give you a little bit of history of mathematics, okay? Because I think this is very important when we study circle. That's the most important parameter uh, for studying circle, okay? So the topic for today is it's the how to estimate pi, right? Some a little bit of history of mathematics. Okay. So first of all, I want to give you some warming up exercise because at some point we need that. So let's go from an easy one, warming up. Okay, first one. Suppose I give you a rectangle, right? So this is A, B, C, and D. So suppose given that A, B, C, D is a rectangle, and it could be in general, can be a parallelogram. It's the same thing. So in general can be the parallelogram. But we don't need that today. So today we only need that to be a rectangle. So that's why I only give you the picture for rectangle. All right. And then you pick a point, any point from the AB. E is just any point. It doesn't have to be the midpoint. Okay, it doesn't have to be the midpoint. It's just any point. So and I connect this one and I connect the other one, right? And then I want you to prove. So it's actually very easy. So it's just a warming up. The triangle of CDE, the area of the CDE is the area of the triangle of the ADE plus the area of the triangle of the CBE. Okay, so let me give everyone a minute. I think you can do that, right? So, right. So the first one is actually here. So let me just uh, shade that, right? So that's a black one here. And then I can use another shade. Let me use maybe the green ones, right? The green one goes here. So it says that uh, the area shaded with black, right? The black area is equal to the sum of the other two green triangles. Okay, why they're the same? I think many of you know this already, right? But let's see why. Or again, it's not easy, right? It's not hard to prove. It's very easy to prove, right? Why? You just need to list their right. You just need to list the formulas, right? The formula for finding the area. So let's see. Let's do this. Okay, let's do this. Very easy to prove. Okay. So first of all, okay, if I want to get the area of A, B, C, D, right? Suppose it's a rectangle, all right? Don't worry about the parallelogram; it's the same thing, right? So and then the area will be I will get the CD, the base, and times the attitude, which is CD, and then the BC, right? And then I can write that to be 2 times where I get a 1/2 here, and then CD, and plus the times the BC, right? I can write the 2 times here, but what is this guy? Well, this guy is just a triangle, right? It's just a triangle, area of the triangle. So this is the area of that triangle of the C, D, and E. So you say that where the area of the entire rectangle is twice of the area of that triangle. So what does that mean? Well, that just means that if you subtract the triangle from the other side, so if I got the A, B, C, D, the area of the whole thing minus the area of the triangle, right, equals the area of the triangle. Does that make sense, right? Because the right-hand side originally was 2, twice of the area of the triangle. I just move 1 to the left-hand side, right? But what is this? If I get that one here, well, these are just the green triangles, right? The sum of the 2 green triangles. So this is just let me write down here the area of the ADE and plus the area of the CB and E, right? So far so good. So that's easy. Okay, very good. Now let's see. First of all, I need to define the pi. So what is a pi? How do you know pi? How do you define pi? You have to define that, right? And then the people just say, well, so I'm going to give that definition for the pi. Where before I give the definition of the pi, maybe I should maybe I should wait a little bit. I have to show you one thing, okay, before we give the definition of the pi. So the first thing is that basically for any given circle, okay, for any circle, I'm going to show the following: the circumference of a circle divided by the diameter of the circle. I want to see the ratio. Okay, I want to see the ratio. So let's see. All right, I want to see that ratio. So suppose you give me a circle. What is the ratio of the circumference of the circle over the diameter of the circle, right? And some people might say, oh, that's pi. Well, wait a second. Just pretend that we don't know the site, we don't know the pi yet, right? I just want to walk you with how human being develop the value of the pi, right? So just wait. So don't suppose we don't know, all right? So and you might say, well, what happened if I have a bunch of circles, right? For any circle, the circumference of the circle divided by the diameter of that circle. Why this is always a fixed number, right? This is a fixed number. This is a fixed number, fixed real number, right? Why? Right? I want to show. I want to see why. Why it's a fixed real number. So let me give everyone some time. So suppose I draw a picture. So suppose this is a circle here, and I got another circle, right? And the two circles have the same center, right? So you're going to prove that for the bigger circle, the circumference divided by the diameter is equal to the same ratio with that small circle. That's what I want to do. Does it make sense? Right. So I give everyone a minute. How do you prove it? So first of all, I want to prove the following. Well, this is the let's say, suppose you have two circles with the same center, right? And then you draw the OA and OB and intersect with a small circle with A prime and B prime. And then I'm going to form the two triangles. So one triangle is here. So let me use that one here, right? One triangle here and the other triangle is here, right? And the two triangles are similar triangles. Does that make sense? Does that make sense? So I'm going to say that the triangle of the OAB is similar with the triangle of the OA prime and B prime, right? Why they're similar? Because that's a SOS, right? We get SAS, right? We have the central angle to be the same, and then the two sides, the larger triangle, I have the radius of R, the capital R. The small triangle, I have the radius of the little r here, right? So R divided by R, that's the same ratio, so they are similar. And if they're similar, then I can do the following. I can have the side of the AB divided by R and equal the side of A prime B prime divided by the smaller r. Does it make sense? Right? But keep that in mind. This is not just true for this pair. It can be true for many pairs, right? As long as I just make a, let's pretend that the angle of the AOB is very small. Okay, it's a very tiny, small triangle. And the two triangles have that ratio. Okay, but I can just make a bunch of those small triangles, and eventually I can make a complete cycle, complete cycle. Does it make sense? So what I want is that I can just do the next one here, same thing here, same thing here, next one here, same thing here, same thing here, and so on and so forth. I can do lots of this, right? Each of the pair of the small triangle are very small. The angle are very small, but it doesn't matter, right? I can take, let's say, 1,000 of those pairs, right? So each pair, the central angle is just 360 divided by 1,000, right? And so, but each of them is true altogether. So if I add everybody together, what happens here? If I take a sum of all of those pairs, the denominator, the numerator is the r, the denominator is the r and r. What's the numerator? The numerator, if you add all of this together, well, that is just more or less like a circumference. And you might say, wait a second, they are not, because AB are the straight line segment. But if you make the central angle to be smaller, and smaller, eventually that will become the circumference of the bigger triangle. Does it make sense? So that becomes the circumference. So circumference, I use space here. So take the sum. So circumference of the larger circle, right? And divide by r, that's equal to the circumference of the smaller circle, right? And so that's why the ratio is the same. Everyone's okay? So I just actually prove it. It's a right. So because that one is a fixed number, then I can do the definition. I can define. So let's define pi is equal to that ratio. Okay, is equal to the circumference of a circle divided by the diameter of the circle, right? Why you can do this? Because no matter what the circle is, the circumference of the circle divided by the diameter of the circle is a fixed number. I don't know what the fixed number is. I just call that pi. Does it make sense? So that depends on the first thing here. So I get the circumference C here. Diameter, let me call that diameter or the 2r. So I can get the C is equal to 2 pi r. So many people thought it's a formula, but it's actually a definition, right? If you look at all of the textbook, they all say that it's a formula. It's not the formula. It's just a definition for pi. Okay. If you look at the history of the mathematics, right? So that's the definition of pi. All right. So everyone understand that? That's the definition of pi. Now the next thing is that how do I estimate the pi? Right? How do I estimate the pi? That's the topic for today. Okay. So let's see. So the first idea of estimate the pi is the following. Suppose I have, let's see, I have a circle here. Let's see, right? And then let's assume that we have the inscribed circle, right? Let's assume that we have the inscribed circle. So I'm going to do this one. Let's do 1, 2, 3. Let's do that for 6 because 6 is easier to do it. So I got the, so I have the inscribed the regular polygon of 6 sides, right? So this is 6 sides here. Everyone's okay? 6 sides here. And I know that the circumference, right? The let's say the circumference C all right. I know that the circumference of C, the cycle, should be bigger than the circumference of the any inscribed regular polygon, right? So it should be bigger than the circumference of the cycle, right? Should be bigger than the circumference of the regular polygon polygon of 6 sides, which is inscribed in the unit circle in that circle, right? And on the other hand, it should be smaller than the bigger one here. So if I have another one, the circumscribed, right? Like that one, right? And like this one, right? And then we get this one here, and then we get this one, and then we can get another one. So this is another regular, right? This is another regular polygon of 6 sides, right? But one is inscribed, the other one is circumscribed, right? One is outside, one is inside. Does it make sense? Does that make sense? So that's a circumscribed circle, right? Circumscribed. And then you can see where, so assume that this is one, right? Assume that this is one here. So let's see, what is this guy here? The circumference of the circle is 2 pi r, that's here. How about this one here? The inscribed hexagon had the length of 1 just because each of the triangle is an equilateral triangle. So this side is equal to 6, right? How about the other one here? So the other side will be the outside part, right? The outside hexagon. So what's the outside the hexagon? Where it's not hard to do it. So I just let's see. Let me do it in this way. I'm going to connect here. Right? I'm going to connect here, and I can just join in this way here. So by the way, this side is equal to 1, right? So let me so this side is actually 1, right? So from here to here, that's equal to 1. And this is a right triangle, and that's a 60 degree, that's a 30 degree, right? No problem of that. And therefore, so can you tell me how big is this? How big is this? Where according to what we did earlier, we get the we get that triangle. So this triangle has a ratio. Let me write down here. All right, so if I have this kind of triangle here, if this is 1, this is 2, this is supposed to be root of 3, right? Okay, so if I change this one to 1, then that side, what should I do here? It should be um, it should be 1 over root of the 3. Does it make sense? I just divide the original triangle here. I just divide each side by root of 3, so that I can get this guy becomes 1, right? And the top guy becomes 1 over root of 3, right? So what is that side here? So if I talk about the outside hexagon, right? Each side will be twice of that. So it will be 2 over root of 3, and we get 6 of this, right? So far so good. So let's see, what is this? If I just work on that one here, so that gives me this is actually 2 times 3, 3 divided by 3, so we can get the 4. Let's see. Wait a second. I think 3. Right? Okay. So it's actually it's actually 4 root of 3. So you divide both sides by 2. So pi is bigger than 3 and smaller than 2 root of 3, right? 2 root of 3 is 3.464, right? And you might say, well, that's too bad because I know that the pi is roughly 3.14, but now your estimate is very, very weak, right? It's very weak, right? You can only tell me that the pi is between 3 and 3.464. That's not good, right? That's not very good. But anyway, so this is just a kind of idea of how people, many years ago, right? Thousands of years ago, how people estimate the pi. That's just the first step, right? That's just the first step in history, right? And now, today, I'm going to give you some more detail. How do you do something better than this? Okay, I'm going to do that better. Okay, so good try, but not very good right now. So I'm going to do a little bit better. So another, I only do another better. How to do that a little bit better. Okay, so here is the idea. Introduced by uh, a mathematician in Asian China many years ago. So this is the year of 263. So it's or how many years ago? It's 1,800 years ago. So that's again that's very old, right? And he estimated that. So he estimated that the pi is somewhere between 3.14 1024 and 3.142704. That's much better. Consider that that estimate was 1800 years ago. Okay, it's 1800 years ago. So the people, 1800 years ago, they can estimate the pi in that way. I would say that's fantastic. That's really good. Okay, so what's the idea here, right? I'm going to introduce his idea. Okay, so here's the idea. All right. So again, today I don't have much time. I just show you the idea. So let's see. So here is his idea. Okay, idea. First of all, again, it's just like the previous picture, right? Like the previous pictures. I need a regular polygon, that's for sure, right? I need the regular polygon. But then, so let's assume that you have a circle, right? You got the, let's see, you got a big circle here, right? You have a circle here. And then first of all, I have a regular polygon. So let's assume that we have a regular polygon of n sides, right? N start with 6 because 6 is the easiest one. So you can start with 6 here. So what I want is that the first one is a 6, and the next one will be 12, and then 24, 48, 96, and 192. I think his estimate is based on that one here. Is based on that one, somewhere on that side. So basically, you go from the 6 side, and then you want to make it bigger and bigger, right? The 12 and the 24, 48, 96, and at some point, and you get a very good estimate, right? Up to 100, 106, 192. So let me give you the idea. Okay. So first of all, let's assume that AN is the area. So this is the area of the regular polygon, regular polygon of n sides, right? Inside a unit circle. Suppose this is a unit circle, right? And so what you get here is that so let's assume that this is the side of n, right? You get I draw that bigger. In reality, it's actually very small because when n is equal to 48, you can imagine that it's actually very small, right? But just because it's very hard to show you the geometric position of those lines, so I have to draw them bigger so that you can see this, right? So like that, right? So that's the n gun here. So this is for n gun, right? And so this is for n, this is for side n, right? This is for n here. And then for the 2n, basically cut that into half. So you go from here, you can get something like this, like that, and like this. And let me use a different color. Maybe use a green, okay? Maybe use a green. All right, so let me. So one kind of polygon use black and the other one use green, so that you can see the difference. That's a green here, and this is a green here, and so on and so forth, right? And his idea is not like the previous one. The previous one is using the circumference, and he said that let's try to consider the area. All right, let's consider the area. So first of all, he's going to show the following. So here is a theorem. Okay, the theorem is that, let's see, the theory is that the area of the unit circle, the area of the unit circle is bigger than the area of the regular polygon of side n. Or certainly that's easy. This is easy. Everything's okay because no matter how you draw the inscribe the regular polygon, it's always inside that circle. So the first inequality, it's easy. That's obvious, right? But the second inequality, that's very clever. Okay, the other one, it says that I have 2 times a of 2n minus a of n. This is clever. This is very, very smart. Okay, so let me explain that to you. All right, so you have the regular polygon, right, of side n, right? So that's your previous step. And then you have the next step, right? The next step will be you make the number of the side double that. Like you go from 6 to 12, right? You can double that, right? And then how do you get the upper bound, right? The lower bound is easy. Everyone knows that, the lower bound, because the circle is bigger than the regular polygon. But how can you get an upper bound here, right? That's the tricky thing. So here I'm going to show you what happened here. All right, so here's the proof. Okay, uh, here's the proof. The proof use the previous argument here, the warming up. Where's the warming up? It's just this, so simple, right? That's the warming up. So if you have a rectangle here, right? The area of the rectangle is twice of the area of the triangle. Okay, let's see how was that used. Okay, so first of all, where I want to make it, I want to make the area bigger because if you prove the first one is easy, right? The first one, this is easy, this is obvious, right? But the second one, I don't know, right? Why the second one is true? The second one basically you want to make an area which is bigger than the circle. Okay, so here's what I want to do here. I want to do the following. For each of this one here, I want to make a rectangle. Can you see that? The rectangle here. And this guy here, I want to make a rectangle. Rectangle here. I want to make a rectangle here. So I want to go over all of the rectangles. And that can finish the rest of them, right? Does it make sense? All of the rectangle here. So basically, you're going to do all of this. And if you just make it outside of a circle, then the total area will be bigger. Does it make sense? So I want to show that the right-hand side is actually the total area here. Okay, so first, let's see why. First of all, I want to see how big is this. Just a triangle here. Well, for those guys, we know that, right? So we know how big is those, right? Those guys are those green areas. So the green areas are, let's see, I'm going to do the green area. Green areas is equal to a of 2n minus a of n. Does it make sense? Right? Why the green area is a big? Well, it's just observation, right? The a of 2n means area of the area of the regular polygon of 2n sides, and an is the regular polygon of n sides. The difference of them are just the cutoff triangles, right? You get the n triangles. They're cut off, right? Okay, but now let me ask you, what is this? If I want to do the red area, the red area, those are the red areas. So how big are those red areas? Well, according to what we did earlier, the warming up exercise, it's the same thing. The red area and the green area are the same. Does it make sense? So that just means that that's the same as the red area. Okay. And now, so how to do this? Now to finish the proof, the area of the circle. Let's see. The area of the unit circle is smaller than the area of the 2n, that means it's including the green area, right? It's the area of the regular polygon of two sides plus the red area, plus the red area. Does it make sense? Because if you add the area, if you add the red area, then the area entirely covers the circle. That's just observation. Okay. And this is A of 2n. What's the red area? The red area is here. So that's a A of 2n minus A of n. And then we are done for the right-hand side. Does that make sense? So if you want to estimate the pi, you need a lower bound. The lower bound is easy, but you also need the upper bound. How do you get the upper bound? By using the area of the regular polygon, which is inside the circle. And you can do that, right? So that's twice of this, right? So after you get that, that's twice of that. That goes to here, and this goes to here, right? So that's his idea. And the rest of them is just, work on that. You go from 6 here, you get the 12, you get the 24, you get the 48. Okay, that's the idea here. Okay, everyone's okay? Let me stop for a couple of seconds, 1 minute. And now I'm going to show you the details. And the detail is also very beautiful. Okay. So that's the overall idea. Okay. Everyone's okay? All right, so let's move on. Let's go to the details, right? So how to get the area? Where you have to have a good idea of the recursion. Basically, if you know the area of the 6 side, you go from here, you get the area of 12 side, and you go there to get the area of 24 side, and you go there to get the area of 48 and the 96, and so on and so forth. So you have to get a good kind of a recursion, because 2,000 years ago, you don't have a calculator, you don't have a computer, you don't have a calculator. Everything has to be done by hand. So you have to work very, very precise, right? All right, so I'm going to show you the details. Okay, so here is the details. How to do this? The basic idea is that, again, let's just go the circle here, right? And this is a bigger one, right? This is for the bigger one here. This is for the n side, right? And then this is for the cut here, right? So you cut that in this way, right? Basically like that, right? So this is just like the 2n side, right? This is for 2n sides, and this is for the polygon of n side, right? It's just one of the side, right? So it's a polygon of n side and another regular polygon of 2n sides, right? I want to see the relation between them. Okay, so this is the center here, right? And I'm gonna go from here and from here, right? So basically this is one because it's a unit circle, right? And let's assume that AM, let's assume that let's assume that the AB, so here is my A, here's my B. AB is equal to M. M is given. Suppose this is the previous regular polygon. Suppose this is given, okay? I want to find that small m here. So this is side here, this is side here, m is here. Everyone understand that? I want to get a recursion. So that means if the previous regular polygon, this is side of the previous regular polygon, this is side length, this is side length of the n polygon, right? Inside the regular polygon, right? And this is a side length of 2n side, right? Of 2n regular polygon, right? You need that kind of a recursion so that you can go from one regular side and to get the next regular side. Does it make sense? And then you can just go to the detail again, right? So that's very clever. So let's do this. Well, it's just an easy geometric argument here. So let's see how we can do that. First of all, I'm going to connect this one here. Certainly, this is a perpendicular. I'm not going to prove that. It's very easy, right? By symmetry, you can do that. Very, very easy. And now, so let's assume that this is C here, this is O, right? And this is P here, right? So first of all, I'm going to get so this is M over 2, and this is M over 2, because P is just a midpoint, right? This is somewhere we covered that earlier. Just written, that's what I did here. That's just, all of the problem here are just a warming up exercise. That's why I want to do at the beginning, right? So it's the same kind of idea here, right? So what is called, what is OP? Where OP by the Pythagoras theorem is just OA squared minus the AP squared, and you take the square root, right? OA is just 1, and OAP is just M over 2. Take a square. So far, so good. Does it make sense? Right? So we can get that. All right. And now, what is the CP? Where CP is just the OC minus the OP. So it's just equal to 1 minus M over 2. Take a square. Everyone's okay? Right? Now, I'm going to figure out the AC. What is the AC? Where again, the Pythagoras theorem. AC squared is just an AP squared and plus the CP squared, right? So let's do that. AP is M over 2, take a square, and CP is just the previous one. So it's a 1 minus the root of 1 minus M over 2, take a square, the whole thing, take a square. All right, let me stop for 1 minute. Right, it's just an argument. It's an easy argument. It's all of the arguments are just the Pythagoras theorem. So let me give everyone a minute, so that and then I'm going to continue. Everyone's okay? All right, so let's do it. So we're going to have M, the next one, where it's a M over 2, take a square. Now this guy take a square, and you can see it's just a perfect square expansion, right? It's a 1 square, and then plus the square of the inside part. It's actually 1 minus M over 2, take a square, and minus the 2AB. Does it make sense? So, all right. And now the good thing is that many of the guys are cancel out. So you can see this guy cancel with that guy here. So this gives me the following. I'm going to have the 2 minus, where I want to do the 2. Here is a 1 minus M over 2, take a square. Okay, 2 minus. I want to move the 2 inside that. Where if 2 is inside, then I have to take a square, take a 4 of that, right? So it's actually like 4 times 1 minus M over 2 square. M over 2 square, let me do that then. So it's just M square over 4, right? So it's M square over 4. So that, what is that? So that is actually 2 minus, okay, I got the 4 minus M square. So far, so good. Everybody's okay? So that's a connection between the, keep that in mind, this is a small m squared, right? That's a connection between the side of the previous regular polygon and the side of the next polygon here, so that you can get the recursion. But that's not good enough yet, because if you just do like that, that's still very tedious, right? Because each time you're going to take the square root. And then when you do that a number of times, you will get the square root, square root. And you can imagine the computational part is just awful if you just do like that. So they are going to do something a little bit better. So I'm going to do just give me a second. You can actually, you can have the following. So if you just do the 2 minus M squared, basically I move the M squared to the right hand side. So I get this to be 4 minus M squared here. And then I'm going to write that to be the square root of 2 plus 2 minus capital M squared. And that's much better. All right, so let me see what is that. So it's a recursion from the side to another side. But if you just work on the side, it's very, very tedious. It's very hard. But the smart part of the person knew is that he used a recursion not just based on m, it's based on 2 minus m squared. Can you see that? So this is a 2 minus m squared, and that's a 2 minus m squared, and that's the recursion between them. All right, so let me just show you what's going on here. All right, so basically that's a recursion we need. All right, so let's do this. I don't have much time. I just give you the idea. Too bad that we don't have enough time to cover this. So here is the n, and here is the m, and here is the 2 minus m squared. So we start with the 6 here, 6 side, 12 side, 24 side, 48 side, 96 side, and 192 side, basically. Where if it's 6 here, we know that at the beginning, right? 666. So the first one was just 111, right? So m is equal to 1 for the first regular polygon, right? And then if we have the 2 minus 1 square, so that's actually, so it's a 2 minus 1 square, that's equal to 1. Okay, how about the next one? The next one, I'm going to just use the recursion, right? What's the recursion here? The recursion says that, so let's look at this one guy here. So it's actually 2 plus the previous guy, that's equal to 1. So that's actually root of 3. Can you see that? So basically, I just work on the 2 minus m squared. All right, so how about to go to the 24? Or if you go to 24, I use the formula again, right? So that will be the 2 plus the previous number, which is the root of 3, and then I take a square root. All right? And then how do I simplify that? Actually, this is not bad. You can simplify that. So this can be written as 2 over 4 plus 2 root of 3, take a square root. So this is 2 here, root of 3 plus wait a second, I think plus 1, take a square and square. So the numerator is the root of 3 plus 1 and divide by 2. Can you see that? And you can get that. And the next one, you just do the same thing. And as you can imagine, it becomes more and more complicated. But eventually, up to 192 side, and you eventually were successful to get a number. And after you get those number, you can just plug into the formula to get the area. And after you get the area, basically, eventually you use that one. So that's a final. Finally, we don't have time. Finally, they use this. So if you use that one here, basically that gives you the estimate for the lower bound of the pi, the upper bound of the pi. Does it make sense? So eventually he get his answer. All right. So we don't have time to finish all of this. But anyway, you don't have to know the rest of them. It's just a very, very tedious for the rest of the part. Okay. I have my notes here, but we just don't have time to cover all. Okay, I have to stop here. Uh, Questions? Any question? No question. Well, today everyone seemed to be very quiet. Uh, we don't have a quiz, but we will have homework. Yes, we will have homework. I will send you homework. Okay. For today, maybe it's hard to make homework because they're just like a research, right? It's a research question. It's a very important question in the history, right? How do you estimate the pi, right? So for today, the homework is very hard to make. But for the previous time, I could certainly do it. I just need time to do this. All right. So that's all for today. Let me finish it. I'm going to end the meeting and see you all next time. For today's work, if you don't understand the detail, not a big deal. I just want you to know, how this works, right? How this works. It's a good way to understand, how the people in history can do those work. It's just amazing. That happens thousands of years ago. All right, see you next time.
Thank you.
Thank
Yep.
you.
Bye.
Thank you.